You're not going to do it here. So if we look at this equation, we have dinitrogen pentoxide. We're heating it. We're decomposing it to nitrogen dioxide and oxygen. So again, you should remember from stoichiometry, 2 moles of dinitrogen pentoxide. When heated, it'll give us 4 moles of nitrogen dioxide and 1 mole of oxygen. When holding all factors constant except concentration, the rate of reaction is proportional to the concentration, i.e., more concentrated it is, the faster it goes. So we can say the rate, and this little thing that looks like a figure 8 on the side with half of it missing, like a funny fish swimming, means it's proportional to the concentration of the reactant, N2O5. The brackets around N2O5 mean concentration. We want to get rid of that proportionality symbol. We want to put an equal sign in there. To do that, we need a proportionality constant K, which is called the rate constant. So the rate of the reaction is equal to some constant, some number, times the concentration. For reaction A going to products, we write an equation. The rate is equal to some constant times the concentration of A raised to the power of N. I'll get freaked out by all the letters. That's called the rate equation or rate law. The exponent N is the order of the reaction. If N is 1, it's first order. If N is 2, it's second order. And we'll explain what that is in a minute. We have to determine N experimentally. There's no way of looking at an equation and telling you what N is. You have to actually do an experiment. It's not the same as the coefficient. So you can't look at the equation. None of those numbers in the equation had anything to do with N. So if we have A and B going to products, the rate equation is rate is equal to some constant times the concentration of A raised to the N times the concentration of B raised to the M. Again, these have to be determined experimentally. So if we look at this equation, again back to methane, the rate equation, the rate would be K times the concentration of methane raised to the N times the concentration of oxygen raised to the M. Okay, we're just dealing with reactants here, not products. Knowing the rate equation and order helps industrial chemists determine the optimal condition for preparing a product. So what if I did determine that it was first order with respect to methane, second order with respect to oxygen? So now I'm doing this reaction. If the concentration of both of these is 1, all right, I put 1 in here and 1 over here, I get the rate is equal to K times 1 to the first times 1 squared, which is 1, right? If I were to double the methane, the rate would be K times 2 to the first times 1 squared. 2 to the first is 2 times 1. The rate would be twice as fast. Right? So it goes twice as fast. But instead of doubling the methane, if I double the oxygen, this would be 1 to the first times 2 to the second. 2 to the second is 4. the rate would actually be 4 times faster. So if I'm in industry, if I'm making a drug product, if I'm over at Grifols or Novo Nordisk, and let's say it takes 8 hours to make the drug, if I double one of the reactants and it goes twice as fast, it'll only take 4 hours. So I can make twice as much drug because the rate is. But if I double the other one, it'll go 4 times as faster. So instead of taking 8 hours, it'll only take 2 hours. So I can make 4 times the amount of drug. That would be nice to know, because if I can make 4 times the amount of drug in the same period of time, I'm going to do what? I'm going to what?
Make it the faster way, as long as it's made right.
Make more money. Thank you. Remember, money is always the one of the things to think of. So it's helpful to know what happens when you change the concentration to the reaction rate. Now say this was an exothermic reaction. So exothermic reaction is going to do what? Give off heat, right? I may not want it to go 4 times faster, because that could lead to loss of control. I could, if I have a very volatile solvent in there, I could boil it off because I release the heat too fast. So I create gas, which creates pressure, which ultimately creates an explosion, which is frowned upon. So knowing the kinetics and the thermodynamics can help us optimize our production. So write the form of the rate equation for oxidation of ethanol. And they didn't write that here, but it would be C2H5OH oxidation plus O2 always goes to CO2 plus H2O. And I didn't balance this. I'm not balancing it on purpose, but you could balance it if you want to, but we're not interested in that right now. The rate equation only applies to the reactants, the ethanol and the oxygen. So the rate is equal to some rate constant times the concentration of ethanol times the concentration of oxygen. It says it's first order in ethanol. So that means the exponent for ethanol is 1. And it's not written, it's understood to be 1. And it says it's third order in oxygen, so it's O2 to the third. So if I want this to go faster, obviously I could increase concentration of either one. Which one would make it go the fastest? Oxygen. If I double the oxygen, what would the rate increase to? How much? Nope. Nope. Too slow, too fast. What's 2 cubed? 2 squared is 4. 8. Thank you. You go 8 times faster, which may be good or may be bad. Yeah, double it means I would put a 2 there, so 2 to. And if you've ever had like a charcoal grill or something, and you open up the vents and let more oxygen in there, whoosh, burns really fast. Where we got the 3 from? This is right here. The reaction has been experimentally determined to be first order in ethanol, so that means this is a 1, and third order in oxygen. makes that a 3. The overall rate reaction is the sum of the two exponents, so this would be 4, the overall, but we don't usually have 4s. Reactions are usually first order, second order, maybe third order. So we're not going to go into all the different ways to do kinetics with rate reactions. That's for 151. So now we're going to go to equilibrium. Equilibrium reactions are reactions that don't go to completion. When they go to completance, all reactants have been converted to products. Equilibrium reactions are also called incomplete reactions, seen with both chemical and physical processes. After no further observable change, measurable quantities of reactants and products remain. Okay? So it's an equilibrium thing. That means reaction goes in both ways. So dissolved oxygen in lake water, stalactite and stalagmite formation, or sugar dissolved in water. So you can dissolve sugar in water, sugar in water, sugar in water, and it'll come a point where there won't be any more sugar dissolved in the water. That doesn't mean it stops. What it means is some goes into solution, some comes back out of solution. It's dynamic equilibrium. But anytime you measure it, there's going to be the same amount of solid sugar and the same amount of sugar in solution. So when we talk about a reversible reaction, we use a double arrow, which means it goes in both directions at the same time. The rate of the forward process in a reversible reaction is exactly balanced by the rate of the reverse process, the dynamic equilibrium. So to illustrate this, okay, she has 10 $1 bills. I don't have any. She gives me one. Now I have one. She gives me one. Now she has, I have. She gives me one. I have. She has. She gives me one. I give her one back. She has, no, 7, and I have 3. She gives me one. I give her one back. She has, I have 3. For the rest of eternity, she gives me one. I give her one back. She's always going to have, I'm always going to have 3. We've reached dynamic equilibrium. No matter when you stop and count, she's going to have 7. I'm going to have 3. Notice I didn't stop at 5 and 5. It doesn't always stop in the middle. But we've reached dynamic equilibrium. We didn't stop giving each other dollar bills. But the result, end result, is always going to be the same. So if I add 2 to 3 grams of sugar into 100 mils of water, all of it will dissolve in a short time. So I have the sugar solid going to the sugar aqueous. No problem. If I take 100 grams of sugar and 100 mils of water, not all of it will dissolve. So you can say, all right, we're done. It stopped. Nothing's happening. Wrong. It's still going on. So individual sugar molecules are constantly going into and out of solution, but it happens at the same rate. Okay? So the sugar solid going to sugar aqueous, it's equilibrium reaction. Okay, one easy way to see this is you have bottled water. Now, okay, you just have a certain amount of liquid water in the bottle, and you got the cap on it. And you could go out in the cold weather, and you'll see droplets of water on the inside, but you didn't add any more water to the bottle. Where does droplets come from? Well, it came from the water vapor inside the bottle condensed out on the side. But continuously, water vapor is going into the air and coming out. Okay. Remember we talked about ice cubes in your freezer. Over a period of time, if you don't have automatic defrost, frost builds up on your freezer, inside of your freezer, because it goes from a solid to a vapor, back out to a solid. But that process is always occurring. So it's an equilibrium until you finally got a certain amount of frost and water, and it won't stop, reaches dynamic equilibrium. So continuous change is always taking place. So here we have nitrogen plus hydrogen to give us ammonia. You mix the components at an elevated temperature. So you're going to have some collisions. You're going to break some nitrogen-nitrogen and hydrogen-hydrogen bonds, rearrange it, and you get ammonia. It's a reversible reaction. Initially, the forward reaction, because all you have is hydrogen and nitrogen, you don't have any ammonia, is fast. You start building up ammonia, some of the ammonia starts breaking back down into nitrogen and hydrogen. And eventually you're going to come a point here where the hydrogen and nitrogen combining to make ammonia, at the same rate the ammonia is breaking down to the hydrogen and nitrogen. So we don't see any net increase in either one or decrease. It's always the same, just like we did with the dollar bills. Always 7 and 3. So we reach a point that no matter how much longer we run the reaction, we're not going to change the amount of ammonia we get. Most organic reactions are equilibrium reactions. It's nice to know when you reach equilibrium. So I come in the morning, I'm working at the factory, and I'm making whatever I'm making. Product A. I set everything up at 8 o'clock in the morning. I do something else. I come back at 4 o'clock in the evening. Sure enough, it's done. It's all right. My procedure started at 8, end at 4. And I have, let's say, 80% B and 20% A left. I reached equilibrium. Is that a good way to do it? No, because what if I reached equilibrium after the first 2 hours? The other 6 hours I'm sitting there just wasting time. And of course, we all know time is money. So we want to know when we reach equilibrium, because it doesn't do any good to go any further. Bless you. So if we look at this reaction, we could do the forward reaction. Nitrogen plus hydrogen gives us ammonia. And we could do the reverse reaction. Ammonia goes to nitrogen and hydrogen. Forward reaction to reverse reaction. The rate of the forward one is some constant, the F means forward, times nitrogen to the N, hydrogen to the M. For the reverse reaction, it's some constant to the R, ammonia raised to the P. We know at equilibrium, the rate of the forward is equal to the rate of the reverse. So we can make a constant divided by a constant is a constant, right? 4 divided by 2 is always 2. So in equilibrium, this is a capital K. These are little k's. Equilibrium constant is the forward divided by the reverse, which turns out it's the concentration of the product divided by the concentration of the reactants. Now, where do we, oh, you see we got exponents there, 2, a 1, and a 3. Where do we get those from? Those numbers come from the equation. If you remember the equation, that was the equation. So the coefficient in front of ammonia was 2, so we have ammonia raised to the second power divided by nitrogen to the first power times hydrogen to the third power. So at equilibrium calculations, the numbers, the exponents, come from the equation. And that'll give you a constant at constant temperature, KEQ. So if I know what concentrations I'm starting out with, I can tell what this KEQ is. Or if I have the KEQ, I can manipulate our reactants to give us the most amount of product. So in general, A plus B goes to C plus D, where the little letters are the coefficients. We can write KEQ is the concentration of C raised to the C times the concentration of D raised to the D divided by the concentration of A raised to the A, B raised to the B. Simple, right? So how do we write these? First of all, we have to have a balanced chemical equation. The brackets represent molar concentrations, molarity, moles per liter. All equilibrium concentrations are unitless. Remember, at the beginning, I always said, for any time of measurement, you need a number and a unit, otherwise it's meaningless. Well, in this case, this is the exception to the rule. There is no units for equilibrium expressions. We can only do this with the concentrations of gases and substances and solutions. Pure liquids and pure solids do not enter into these calculations. So here, hydrogen plus fluorine gives us hydrogen fluoride. First thing we look, there's no solids or liquids, so we don't have to worry about that. So the product is, KEQ is equal to the product, HF, raised to its coefficient, which is 2, divided by H2 raised to the 1 times F2 raised to the 1, because those are the coefficients. Yes? I'm looking in the back. I'm seeing kind of puzzled looks. No? Maybe? Okay, here we have manganese dioxide and acid and HCl going to Mn2 plus Cl H2O. First thing we look, MnO2 is a solid, so it's not going to be an equilibrium expression. H2O is a liquid. It's not going to be an equilibrium expression. That's why I got them crossed out. So if we look at the equilibrium expression, it's the product, Mn2 plus times Cl2, both raised to the first, divided by H plus raised to the fourth, Cl minus raised to the power of 2. Yes? Yes? Okay. So if I gave you those 4 concentrations, you should be able to tell me the equilibrium constant. So if you think about it, KEQ is the concentration of the products over the concentration of the reactants. If the KEQ is greater than 1,000, 1 times 10 to the third, it means the numerator is a lot larger than the denominator. So I have a lot more product than reactant, which is what I want. So I want a large KEQ. If KEQ is less than 1/1000th, that means the denominator is a lot bigger than the numerator. The reactants are a lot greater than the product. So I have mostly reactants present. I don't want that. I'm not selling reactants, I'm selling product. If it's between 1/1000th and 1,000, I have a mixture of reactants and products. That can be problematic, because now I have to have a step in there to remove the reactants. So that's more time, more money, less profit. So again, we said at equilibrium, the concentrations don't change. So HI is placed in a sealed container, comes to equilibrium. So we have 2HI goes to H2 plus I2. They're all gases. So if we write the equilibrium expression, it's H2 times I2 over HI squared. So we put the HI, we let it come to equilibrium, then we analyze the 3 components. So at equilibrium, we find the HI concentration is 0.54 molar. The H2 and I2 are both 1.72 molar. Why are these 2 numbers the same? Why would they be the same numbers? Go ahead. What's our equation tell me? For every 2 of these, how many of these do I get? 1. How many of these do I get? So I always get equal amounts of these, right? So at equilibrium, whatever this is, this has to be the same. So if this is 1.72, this has to be 1.72. That's what our equation tells us. So now I would go and take those numbers and put it in there. So I'd have 1.72 times 1.72 divided by 0.54 squared, which is 2.96 divided by 0.29, or 10.1. Or for 2 significant figures, it would be 1.0 times 10 to the first, because 10.1 has 3 significant figures. So what this tells me is I have a significant amount of both products and reactants, because it's somewhere between 1,000 and 1/1000th. Or essentially a 10-to-1 ratio. We can manipulate this equilibrium. Le Chatelet's principle, which states if a stress is placed on a system at equilibrium, the system will respond by altering the equilibrium composition in such a way as to minimize the stress. Do I need to say more? Yeah, I think I do. Okay. What's that? Playground, that's a what? Seesaw, okay. So now it's balanced. I got A and B on one side, C and D on the other side. If I add some A, what's going to happen to the seesaw? It's going to tilt. I made a little A, so I added a little bit of A there, okay? I want to get it back to equilibrium, balanced. So I have to take some of this and do what with it? Put it on the other, shift it to the other side. So I got to take some of this and move it this way. So now I'm going to have maybe a little A, maybe a little C. So by adding some reactant, I end up making more product. I had to shift the equilibrium to the other side. Just think of it as a teeter-totter. That's all that Le Chatelier. I applied a stress by adding A to one side. To relieve the stress, I shift it to the opposite side. If I had added some more C, it would have tilted in the other direction. So to relieve the stress, I would have had to shift it back towards the A and B, towards the reactant side. So when I add something, it shifts the equilibrium to the opposite side. What if I had removed some CD? It would have tilted this way, right? I would have had to shift back towards the CD, so I would have made more product. If you remove something, the equilibrium shifts to the same side you remove it from. So if you remove product, you generate more product. If you remove reactant, you generate more reactant. When you add, you shift it to the opposite side. When you remove, you shift it to the same side. That's all that says. So if I'm doing a drug synthesis and I'm making, let's say my product is, I have a product that produces a product and water is the other product. I want to make more product. How could I get more product? Two ways. I can add more reactant, right? Or I could remove one of the products. And let's say I'm making an organic that's not soluble in water. It's less dense than water. So I have this side of the reaction, so I have my product floating on top of the water. I want to remove some product. Would it be really easy to remove the water? Yeah, if I had a little valve at the bottom, I could open it up and the water would drain out, so now I'd have less water in there. I'd make more product. This is how we can disturb or change the equilibrium to make our process more efficient. So if I add ammonia to this side, I'm going to shift it this way to the reactants. If I add a reactant, I'm going to shift it to the product. And what you do is going to depend on how easy it is to either remove the product or add reactant. That's basically what that's saying. So here we see effective concentration, red, yellow, and colorless. I'm going to move this down here. That yellow urine color, is the reaction at equilibrium. If I add more Fe3 plus or SCN minus, I'm going to shift it towards the reactant side, so it's going to become more red, which is B. If I add some more red, I'll shift it towards the other side, and I'll lose more of the red color. So I can shift the equilibrium to get what I want. If you have an exothermic reaction, you treat heat as a product. So nitrogen plus hydrogen gives us ammonia, and it releases 22 kilocalories. So if I were to cool that, cooling that reaction would be the same as removing heat, right? So heat's a product, so I'd be removing more product, so I should then shift the equilibrium to the product side. The equilibrium shift this way. So I'd be creating more product by cooling the reaction. Because as I remove this, remember if you remove it, it shifts to the same side. So this would shift this way. So just by cooling that reaction, I can generate more product. Similarly, if I just start it and I don't have an apparatus for cooling it, and the heat builds up, I'm going to be adding product. It's going to shift this way, and your equilibrium is going to have a lot more reactant than product. So if I know this and I'm running this reaction, I'm going to take whatever vessel I'm collecting the ammonia in, and I'm going to have a jacket, a cooling jacket around it, and I'm going to keep it at a certain optimal temperature. So but I also have to know what temperature I need for the reaction to occur. If I cool it too much, I won't get the reaction to go at all. So that's why it's important. You have to know the thermodynamics. You have to know if I cool it, they're not going to move as fast. If they're not going to move as fast, it's not going to, the rate's going to go down. Okay, so you have to balance all three of those things. I have to know what temperature I need to get it going, how fast I want it to go, and where do I want the equilibrium to stop. So there's a lot of things that people have to analyze before they just go out and do something. If it's an endothermic reaction, you treat heat as a reactant. And that's the wrong product. I assume it's NO2, not NH3, because we didn't have an H on that side. 4, 2 NO2, 2N. I'm guessing this should be a 2. I don't know what it is. 2, 2, 2. And this should be a 1. There we go. That's what I'm thinking it should be. But anyways, if you heat that, you'll make more product. So you can kind of think of making popcorn. You know, obviously, if you heat it, you're going to make more popcorn. That's an endothermic reaction. If you don't heat the popcorn, you're not going to make popcorn. If you heat it too hot, you're going to do what? Burn it. Pressure affects the equilibrium only if one or more substances in the reactions are gases. And the number of moles of gases on each side have to be different. When the pressure goes up, it goes to the side with less moles of gas. When the pressure goes down, it shifts to the side with more moles of gas. An example there. So here we have, again, we're making ammonia. If an increase of pressure, which way will it equilibrium shift? On the left side, how many moles of gas do we have? On the reactant side, how many moles of gas do we have? 4. On the right, we have 2. So as we increase the pressure, which way is it going to shift? Oh, it'll increase towards the 2 moles. So if we want to make more product, we increase the pressure of the reaction. The bottom one, HI goes to H2 and I. Again, in this case, we have 2 moles on each side. So increasing or decreasing the pressure has no effect on it. Okay? And that was it.